Welcome back. So now we're going to continue with Marc. Hello, Marc.
Hi, Santiago.
How are you?
Pretty good. How are you?
Oh, good. Where are you streaming from?
I'm currently based in Hamburg, in Germany,
Oh,
from
nice.
the fourth floor of my apartment. So nice view out in the green.
With a nice standing desk.
Yes, exactly.
Okay, so you are gonna talk about how to speed up deep learning development life cycle for cancer. If you are ready, we can start.
Yeah, sure. I'm ready.
Go ahead and good luck.
Thanks. All right. Hi, everyone. My name is Marc. I have a background in computational neuroscience, and currently I'm the CIO at a company called Mindpeak. So my talk is about speeding up the deep learning development life cycle for cancer diagnostics. What do I mean by that? I want to tell you a little bit about how we handle things at Mindpeak and what we learned over the years and how we managed to make experiments in deep learning quickly. First, a little bit about Mindpeak. So our mission is to increase the cancer diagnostic accuracy and make it accessible to everyone who is in need. That's quite an ambitious goal. And so, pathology, what is it about? Well, you might think pathology is about dead people, but in fact, it's a lot about living people. In fact, pathologists are very crucial in the chain of cancer treatment. So, if someone goes to the doctor and a tissue is taken from, say, the breast or the lung, that's sent to a pathology lab. And then they prepare that tissue, this biopsy that you see here, and the pathologist will look at it under the microscope. And then the pathologist, with his years of experiments, makes the diagnosis. And that diagnosis, in turn, is sent back to the general clinician that sent in the biopsy in the first place. And the clinician then decides on the treatment. So the diagnosis of the pathologist is really what determines the treatment in the end. So it's super important. Now, here's the problem. We have a rising demand of pathology diagnostics, but the number of pathologists stay roughly the same. So more and more diagnosis needs to be done by more or less the same number of people. And that's a problem, right? Because I'm sure no one of you wants to be in the position that you're in need of cancer diagnostics and you need to wait for months. So that's where we want to step in and we want to help reduce that gap. So this is how we envision the cancer diagnostics flow tomorrow. We want to have digital scanners that scan these tissue probes instead of looking through the microscope. Then immediately after scanning, an AI can do a pre-analysis, make a diagnosis, and then when the pathologist opens the case, they can check on the screen what the AI did. They then can take a look and say, yeah, I agree, or I don't agree so much. And then if there is a disagreement, we can even use that to improve the model further on. So in total, you can say that Mindpeak deals with automation tools for visual diagnosis in pathology. That means we always work on images. So this is always images taken from body samples. And we use state-of-the-art deep learning tools on it. And we don't want to replace the pathologist, but we build tools that we give to them so then they can make more reliable, more reproducible, or faster diagnosis. And here's some excerpt of our partners. We have great partners, many nice labs, industry partners, and so forth. We have a fantastic team, very cool people. We're here in Hamburg, in Germany. And this is us on a nice boat trip that we did some time ago, and some of our advisors and investors on the slide. So one example application that we developed is this cancer cell detection for immunohistochemistry. So here you see an image of what is called a Ki-67 staining. It's a staining that marks cells brownish if they're in the process of proliferation, so if they're dividing. And that means they're growing, right? And so this is one key tool used by pathologists to determine cancer growth. Now, the task of the pathologist here is they need to count the number of tumor cells, and then they need to look at the threshold of positive tumor cells in combination to negative tumor cells. So the ones that are active by this marker and the ones that are not active by this marker. And this is, of course, a manual, tedious task where you need to count each individual cell and determine that. So what I plotted here now is the result of our AI. You can see there are little dots that now found the different cells, and there are yellow dots for negative tumor cells and red dot for positive tumor cells. And so this way, the pathologist can get a much faster result and doesn't have to do the manual counting. Now, this might look easy to you. I mean, it's easy to detect some brown, right? But in fact, the variation in the labs is really huge. So there are many different use here. So as you can see, this is maybe an image taken more from a microscope camera. And all these images here, they're all Ki-67 stainings. So you can see it's not an easy problem we're dealing with. In particular, this happens because each lab has slightly different chemicals and is working at different temperatures, and that's how these different shapes come about. And our model needs to be able to deal with all of this variability. That's also one big thing that differentiates us to some competitors, because we try to develop a deep learning model that covers all this variability. So one model for all labs, and others build models, one model per lab. And we think it's better to have a more general model, because then you're not so prone to overfitting. You will generalize better, because if you just fine tune to one specific lab, there's always the risk that you overfit a bit. Now to the focus of the talk. This was a bit of the background of Mindpeak. So I want to talk a bit about this deep learning training cycle. Usually you start off with some idea, and then you collect some data and have some annotations on them, and then you move on to the implementation phase. You write some code, you develop your models, your losses. Then you go ahead and train the model, usually on a GPU, and then you evaluate it on a test set. Now, if your results on the test set look promising, then you might deploy it, and then you need to monitor if it's actually doing what you think it's doing in production. And then often the cycle continues again. You then collect some data again from the things you've seen in production, and you annotate. Maybe you change some things. And now the question today is, okay, you always need to do these experiments, and how can you make that as fast as possible? So the focus is on this end here. How do I go from idea, implementing it, to having a fully conclusive result and being able to tell if it's actually improving my previous model? So let's dive in. The goal is to test ideas as quickly as possible. So we'll start with the idea stage. And that one, first, of course, in the idea stage, you need to generate an idea, right? And you can either do that without data, so when you start fully from scratch, or you can do it data-driven. And you should also think about how you annotate, how you have efficient annotations, and you should define some metrics. How do you measure that you reach the targets you want to reach? So some say brainstorming is fantastic, and some of the best ideas are found through it. And I agree, it's good, but I think it's important how you apply it. So what I don't think is so good is if you just throw ideas in a room, no limits, and just write them down, because that often leads to what's called groupthink, where you don't generate too many distinct ideas, but rather they are all very similar. So what we usually do is every person of the team sits down by themselves. You take maybe 20 minutes to generate your own ideas. You think about the problem. You think about, how would I tackle this? And then after some time alone, then the team gets together, and everyone has 1, 2, 3 minutes to present their idea on one slide, maybe. And then after that, you look what are similarities, how do ideas overlap, and then you organize and group them together, have a short time box discussion about it. And then it's crucial that you do a voting. So every member gets a few voting points, and you can vote on the best ideas. And if they're limited, then you really need to decide. Otherwise, it's often you have many cool ideas, and it's not really clear on what you should work on. You can also use something called the business model canvas to further evaluate this in a more business context, but that's usually more on the business end and not the engineering part. All right, what if you have data? Well, if you have data already and you already have your first model trained, then you should use your data to drive your ideas. That's much more telling than just thinking about ideas out of the blue. So what can you do? You can take a subset of your validation set and you look at the errors your model is doing on this validation set. And you categorize those errors. And then you can see where are the most errors happening. And that is probably the category you should focus on because you can get the biggest improvement from there. Let's take an example. So remember our problem, we need to detect these cells and we need to classify them. And now I might say, oh, I'm worried that maybe we have a lot of stroma immune misclassification. So these are different types of cells, different classes. And if I just go about and I have this intuition, then I could try to create something to fix the problem. But now instead I sit down, I make a small list, I go through 100 images and I mark each time on an image this problem occurs with an X. But I also do the same thing for other categories in the meantime that I note other errors. Now, if you come up with these counts here, of course, you see, okay, so stroma immune only happened 4 out of 100 images, while something like scan artifacts maybe had happened 35%. So probably my time is best spent focusing here rather than focusing on this problem. Makes sense, right? Then if you have your idea, you should collect data often. So you should think about how to efficiently do that. In our case, you could say, okay, I let pathologists mark the segments of each cell, so they should draw the borders of the cell. And that's one possibility. But instead, you could also say, okay, they just have to mark the center of each cell with a dot. And that way, we also know where the cells are, because for our problem, it's important to count the cells, but not to find the exact segmentations of them. So maybe this way would be much more efficient, and you would get your data faster. Now, let's quickly talk about metrics. So metrics, of course, define your goals. And often you have several goals. You have several different metrics, especially if you work on real life problems and in pathology in particular. And so still, I would recommend to try to single it down to one metric that combines everything. Because if you don't have that, then it's always the question, how do you compare? So you have one model and another model. How do you tell which one is better? Maybe the one is better in one metric, the other is better in another. And it's then in the team, it's really hard to tell how to judge when a model is considered better than the other. And you might even disagree. One might say, but this is more important. And the other says, no, I think this is more important. So upfront, just decide on a clean single metric. And how can you do that? Well, fourth, you can make aggregates. For example, if you have precision recall problems, you can aggregate them as the F1 score, which is the harmonic mean of precision and recall. You could have a weighted average of different submetrics. So that just means you decide on the weights where you think what is the importance of each metric, and then you just make this weighted average. If you think some metrics are equally important, the min operator could be something you can look into. That way, if one metric gets much better, but the other one doesn't or even suffers, you will not improve the model. And that might be beneficial in some constraints. And if you have the single metric, of course, you will use that to validate your ideas, because you will always use it to compare if your idea helped in comparison to the baseline. The submetrics can help you figure out where to improve, figure out, okay, the subpart, this classification part is not so good, maybe, and then I should look at my validation set for errors and try to generate the next ideas again. So for Mindpeak, one example here. So we have cell detection as one metric. We need to find where are the cells. And for that, we use precision recall. So we combined it as the F1 score. And then we also need to classify them. So we use the detected cells and the original image to feed the classifier. And that one determines what's the class of each cell. And there we potentially have many classes. So we also use precision and recall, but for each class separately. And then we have a weighted combination of these different F1 scores for the overall F1 score. Now you might say, but it's still two metrics. Yeah, that's true. So the target metric in the end will be a combination of both of them. So you combine them together, weighted or something like that. And that's the goal you're measuring towards. Okay, that's it for the idea stage. So to recap, you should think about efficient annotations. You should have a single metric that guides your experimentation. You should use your data to drive the ideas. You should track the errors your current model makes, especially in categories, so you can figure out where to improve in the high error categories. Then let's move on to the second phase, the implementation. Now I have my nice idea and I want to build it out in code. So for the implementation stage, the thing that's very important for me is code quality. If you have high code quality, then usually you can iterate fast, right? You look at your code, you know where exactly you need to change something to try out a new idea. If your code is messy and you need to touch a lot of different moving parts, then it's much more complicated and you will have a much harder time and thus just take longer, introduce more errors. So my rule of thumb is whenever you touch code, think about, can I make it a little bit better? Do some small refactoring. If you do that way, it feels effortless, more or less, just a tiny improvement every time. And then, of course, use things like typing and linters, the typical software engineering quality things. Furthermore, use automation, take advantage of CI pipelines. I will talk a bit more about that soon. Then you should use profiling. You want to make sure that your code is running as fast as possible. And in deep learning, it's in particular important to figure out the interplay of CPU and GPU usage, because it might be, for example, we had that at some point, that metrics calculation for validation metrics or so take a lot of CPU resources, and your GPU idles around a little bit in some phases. And that's really wasted time. You want to make sure that your GPU is always maxed out. And the NVIDIA Profiler Insight can give you nice graphical visualization of your code running. And you can see exactly when was the CPU used and the GPU used, and when was data transferred back and forth, because that's also another potential pitfall. Lastly, in the implementation stage, reproducibility is super important. You want to know exactly when you run something that you can reproduce it and that you know exactly what data has been used. So some examples for code quality. As I think as I said, it's very important. So one thing I really like is comments as code. So say you have this loss function here where you do something, namely you filter out the background targets, and someone wrote this as a comment. I mean, now this is simple code. I just made it an example here. In real life, you will have probably much more complicated code and maybe also a longer comment explaining what happens. And what I like to do instead is just don't write this comment and have a small function that explains this. Why is this better? Well, first, it's in code. So if someone changes and refactors the code, it will definitely change because they will need to consider it. Whereas comments often stay stale and they are old at some point. And second, it's easier to read, right? I mean, I have less code here. I just read, it filters the background targets. I know exactly what happens. And I mean, I can look deeper if I want to, but maybe I don't even need to. So that helps me to be faster. And that's our goal here. We want to iterate fast. Second side note on code quality, a library that I really like is the einops library. It's fantastic because in deep learning, you often need to shift around dimensions. And for example, here, we have a prediction that consists of a batch, a channel, a height, and a width dimension. Then there's some permutation happening. Now you need to figure out what has exactly been done here with the indexes. Seems like the number 1 moved to the back, so the channels move to the back. Then you need to look here, some contiguous view of some multiplications, and then the channel. So you can figure out what it does, but it's not super intuitive. In contrast with einops, so rearrange is just einops.rearrange. It's a function where you can say, okay, I want my prediction that consists of batch, channel, height, and width to be reshaped as just a combination of batch, height, width. That's why they're in a bracket, and then the channel in the end. super easy to read. You know exactly what happens. You don't need to overthink that. And what's also cool, you can also add dimensions here. So you can say comma channel equals 3, and that way you enforce that the channel dimension is always 3 in this code. Otherwise, it will fail with an error. I regularly blog about such things. So if you want to check out my blog at päpper.com/blog, feel free to have a look. Then CI pipelines. So I really want to take advantage of automation as much as possible. Of course, for automatic checks, code formatting, PEP8 and stuff like that, linting. Then automatic unit tests is not super popular in deep learning, not as much as in software engineering yet, but I think it's taking more and more the same shape as well. Automated unit tests, super important. I mean, of course, in deep learning, you cannot test every single thing. I think for that, it's too dynamic during training and stuff. But what you can test for sure are your metrics, your losses, and all the data loading and transformation aspects, because those are really essential. If anything goes wrong here, you are just totally lost later on, right? If your loss is miscalculating something, then later in training you might have wasted a lot of GPU power, and you need to repeat everything. So that is really, really essential. We also use automatic Docker builds for the Docker images, so you can easily share and reuse in other environments. And one thing that might also be nice is to have an automatic deployment of a demo or dev model, so you can have visualizations and share that between team members. Yeah, because bugs caught early are the best. Yeah, they save you the time, right? If you see you just committed some code, the pipeline fails, you know, I'll just fix it, and then everything's solved. Yeah, here's an example. We use GitLab CI for that, but of course you can use GitHub or anything else, doesn't matter. Okay, now let's say we have written nice code. We have optimized the performance. We use the profiler and everything. Now we also want to make sure it's reproducible. And in deep learning, it's a bit different than in normal just computer software engineering. You have code, but you also have data. And one best practice is that you really track the data with your code. You need to know what experiment ran with what data. Otherwise, how will you be able to compare, right? If you compare one experiment with another and they use different data, then how can you tell if the idea or the model was the issue, helped or didn't help, or if it was the data? You cannot. So you need to always compare on the same data. What we use is called DVC. It's short for data version control. And it takes care of tracking your data with Git. You can have all your big data. So we have many large files. We store them on a NAS or a cloud storage. And then inside of Git, there are just some meta files that are tracked, and they determine exactly the state of your data. And so you can just, it's very similar to Git. So you can do DVC pull, DVC check out, and so forth, DVC add. And that means if you git check out something, you can git check out and DVC check out, and you know your code is at the state that the data was at that point in time. The other cool thing of DVC is having pipelines. So I made an example here. You can generate a code pipeline where you say, okay, my data generation script depends on my raw data. My data statistics computation script in turn depends on the data generation, and so forth. And if you do it this way, you can have one single command that builds all your data, runs the training, runs the evaluation, and everything in one pipeline. That's really nice. And also, if you change, for example, the run training script, then DVC will recognize that nothing changed here, so it will only rerun from this phase, and everything here is cached. Whereas if you change your data, of course, the whole pipeline needs to be rerun. We also use that to track your metrics, TensorBoard logs. That way you always have the most recent baseline at hand, and you know exactly what you're comparing against. So that really helps not to always have to ask someone else, oh, how was your run? How were the metrics? How's this? You always have the best one checked in and ready to be evaluated. So if you don't use something like that, really check it out. So to sum up the implementation stage, you should push for high code quality. You should really make sure that whenever you touch code, you do some small refactoring if applicable. You should use linting, typing tests, of course. And to do that, you use continuous integration. Profiler will help you to avoid easy bottlenecks. And I should rest my eyes. You have to achieve reproducibility and track your data. For that, I recommend DVC. And let's move on to the next stage, which will be the training and evaluation. So you set up all of this. And now the question is, let's train it. I have my idea, I implemented it, go for it. And now this happens usually. You have to wait. Why do you have to wait? Well, you let it run the training on a GPU. And typically, deep learning is very data hungry. So you have a lot of data and your training takes a while. And of course, that's not so nice if you implemented your cool idea, you want to get feedback quickly because you want to iterate fast, right? You want to see, did it work? Can I tweak it a little bit? Or does it not work at all? Should I move in a different direction? And the longer you need to wait, the more hassle you have because you are stuck and you cannot really know how to improve from the state. So let's fix that. What can you do? You can, for example, use multi-GPU training to gain speed ups. So multi-GPU training is an obvious way to speed that up because you can just parallelize the training. I will get to that in a minute. You can also reduce your data set. So you can look at how can I have less data to train on? Because if you train on less data, of course, training will be faster. And you should have, as we defined in the idea stage, you should have your single metric here as guidance. That one you evaluate to in the end, and that one should guide you if your idea is working or if it's not working. So let's take a look at the multi-GPU training. So for multi-GPU training in PyTorch, that's what we are using at Mindpeak, there is this thing called data parallelization. So assume we have this bunch of training data. I set here 1,632 images because that conveniently splits into 102 batches of 16 images. And let's assume we can run with a batch size of 16 on one GPU. That means we run batch 0, then batch 1, then batch 2, and so forth, sequentially every batch. Now, to make that parallel, you can say, okay, let's use 3 GPUs instead. Then the idea is, okay, GPU 0 can run batch 0 as well, GPU 1 batch 1, and GPU 2 batch 2, all at the same time, while this one only did batch 0. So in theory, you should have something like a 3x speed up, right? Well, not quite. So there is communication overhead. You need to somehow organize this. And also you need to make sure that your model is just one trained model in the end. So also you have to somehow take care that the model is synchronized. Let's see how PyTorch data parallelization solves this. In data parallelization, one GPU acts as the master GPU. That one is able to synchronize with the others. And so here in this case, we have 3 GPUs, 2 workers, and 1 master. The master sends over the data, the batch data, and the model weights for this batch, so that to make sure that every GPU runs on the same model weights. Then each GPU runs independently on its own batch. So here, as you can see, GPU 0 on batch 0, GPU 1 on 1, and GPU 2 on 2. So far, so good. Now they send back the outputs to the master, so the master computes the loss. And then the master scatters the loss again to the workers, and they compute the gradients on each GPU. And then finally, they share the gradients again with the master. The master puts all the gradients together, makes the model update. And now at this point, the model is asynchronized, right? There's a different model here than on these GPUs. That's why back in this stage, you send the model weights, so they are synchronized again. And then the cycle repeats, and everything is good. But as you can see, there's a lot of communication here, right? There's here communication here, here, here. So as you can imagine, this will not be a 3x speed up. It's more like a, I don't know, 2x or 2.2, 2.3, something like that. And of course, we don't like that. And we can do better. That's what PyTorch distributed data parallel can do for us. So in distributed data parallel, you load and process batches fully separately on each GPU. I will talk about that in a minute, how that exactly works, because you might wonder, but before the master organized this, how do they now take care of that? I will talk about that in a minute. But let's assume somehow we have split up the data so that there's not the same batch running on separate GPUs. That would be bad. We have different batches here. Now each GPU computes the loss and the gradient separately, so totally independently of each other. And then this is the only communication stage in distributed data parallel. We have a gradient all reduced, so we share the gradients between each GPU. And then each GPU has all the gradients, can compute the average gradient. And then each GPU updates also independently the model. Now they are synchronized because they started with the same model and they have the same gradients. So they will end up after the update with the same model again. And that way, of course, as you can see, is much less communication. So you are close to the 3x speed up that you want. Now, what did I mean with you need to take care of this? So to do this, you need to implement a special sampler called a distributed sampler. There is a PyTorch implemented one that you can use if you have a default setup, but we needed to adjust that a bit. So you inherit from it and you adjust it to your problem, to your data loading and all that stuff. Basically, it takes care of making sure that each GPU knows what data to look at in each batch and each epoch, so that they don't train on the same stuff, because then that would be not really nice, because you want to train on different data. And another thing to mention is this nice paper of Goyal et al. It's a paper from 2018. They looked at how to train large models with large batch sizes. So over many GPUs, they trained ImageNet in 1 hour. And this paper I would really recommend to look into if you do the multi-GPU training, because you should also take care of learning rate warm-up and learning rate scaling. I won't talk about the details here now, but yeah, it's worth checking out. So if you have already optimized everything, you have multi-GPU training, but it still takes too long, you might consider using dataset reduction techniques. What do I mean by that? Well, one thing is you can shrink your own data, your large data set, and make it smaller, make it a representative small set. So you have 1 million images, only train on 100,000 ones. But it's not so easy to define representative, right? You could do a random sample, but then, for example, in our use case, you have many different variables like labs and scanners and stainers and all that stuff. So it's easy if you do a random sample that you end up with a distribution that is not really representative for your problem. So you risk of losing out on information. But it's easy to do. So if it's possible for your problem, just go ahead. You can then run fast experiments on the small set. And if you have something that looks promising, run it on the large set. Another possibility is to create a toy data set, which is more work, of course, because you need to do that programmatically, but it's highly customizable. You can parameterize it so that you can exactly define how you want some setup. Of course, with the toy data set, there's always the risk that you don't know how it really translates to your real data, but it's very good for idea prototyping. So for example, this is something we created as a toy data set for this cell detection problem. It's super simplified and not doesn't translate to real data at all. But it's a good proxy for experiments. For example, we experimented with label noise, where in pathology, pathologists don't always agree on the exact single cells. So there are definitely some label noise in the data. And we tried out how we can deal with that. And we tried many different approaches. And it really helps to train a run in 1 hour instead of 1 or 2 days. So that was really helpful in finding the right solutions. All right. So then the summary for the training and evaluation stage. Basically, you need to take care of multi-GPU training. You want to have fast training, because if you need to wait a week or even 2 weeks or so for your results, then by the time you get them, you probably have already almost forgotten about it again. And it's super hard to keep track. If you do that with many different experiments, you have results coming in very late, and yeah, it's a pain. So initially, a few years ago, we only had single GPU training, and we needed to wait a week for results sometimes, and that was really painful. So then we implemented multi-GPU training, and now we can train in a day or two. So that's much more convenient. You implement something, you let it run overnight, and the next day you already see if the trend looks promising, and you know if your idea makes sense to look further into or not. So as I said, you can also reduce your data set by having a small representative subset, or you can build a toy data set to simulate your data problem and to make sure that you can really iterate as fast as possible. Just to reiterate, of course, a single metric defined in the idea stage should be your guide pole that determines if your idea is a winner or not. If it's better on that metric, hopefully your idea was nice. If it's not, then you probably need to look into why that's the case. So now we have everything, right? We have our idea, we implemented it, we trained and evaluated it. Now, what usually happens is this. It doesn't really improve over the baseline. And of course, that's sometimes a bit frustrating or disappointing. But you must say, in machine learning, it's normal. You have a lot, you need to iterate a lot. And it's normal that ideas don't work out. But the good thing is, if you did all these tricks and tweaks, and if you have a fast cycle, a fast iteration, then it's really not so bad, because I mean, you know that you can generate the next idea. You know that it's not you didn't spend months of work wasted. You just spent maybe a few hours or a day, and you could try it out. And that really helps a lot. I mean, otherwise, it's much harder to move towards a really good deep learning model, I think. The important thing for me is that you always learn from also the failed experiments. They are very beneficial in telling you why things. I mean, you should try to ask, why did it not work? Often you take a research paper, you implement it, and then you let it run. It doesn't have the results that the research paper promised. Then ask yourself, why did it not work? What's different here than in the paper? Maybe my problem is a bit different, and maybe this doesn't really apply. How can I learn something about my data, about my problem from this experiment? Maybe I can even generate new ideas, something that will help me in the future. And what we often do is that we write a diary entry about our experiments. And that is no matter if they fail or if they work out. That's a very good method, I think. We use Confluence pages for that, but you can, of course, use anything you like. You can just say, what was my idea? How did I implement it? What were the results? And what are the learnings? Did it improve over the baseline or not? If yes, nice, that's good. If not, why not? Why did it fail? What did you learn? And how can you maybe go on with next steps? And that helps not only for yourself, because often later on, a few months later, you have a similar problem or thing, and then you forgot exactly how was it. Then you can look it up in your page, you know, this is exactly how I did it. Okay, makes sense. Then maybe I try it out this way or that way. Much easier. Also for team members, you can share it. If someone asked you about something that you did before, you just reference them to the diary and they know exactly what was going on. So that's awesome. Yeah, to sum up my talk. So what can you do to improve the deep learning development cycle? Well, first, use data-driven idea generation. That helps you figure out the potential categories where you can improve the most. And of course, improving a lot is what you want to do in deep learning. You should have a single evaluation metric to target so you don't get confused. It's easy to communicate in the team. It's easy to have a direct comparison between ideas. You should strive to automate everything. That means use CI pipelines to have automated tests, especially for the very important things as losses, data processing, and so forth. And you should track your data with your code. Use something like DVC. There are probably a lot of other tools that you could use as well, but we use this one and it's really nice. Yeah. Then you should take advantage of high code quality. I gave some examples, Commons as Code and the einops library. But of course, the most important thing is if you touch code and it doesn't look too good for you, do a refactoring, make it a bit better. That way you help out your whole team and you strive towards having much better code, much more high quality code, and you can iterate faster and it's more fun to work with. Also take advantage of multi-GPU training. And if you do, don't waste your time on data parallel, use distributed data parallel. Even the PyTorch documentation nowadays mentions that. I mean, there is some merit to this. So this is super easy to do, the normal data parallel. You need to not set up anything. There's no distributed sampler that you need or stuff like that. So if you just want to have a low effort multi-GPU training, of course, you can also do that. But if speed is of importance, really consider this one. And lastly, you should take advantage of learning opportunities. And that's regardless whether your experiments worked or they didn't work. Always think about what can this teach me about my problem, and then generate nice ideas from there. And if you do all of this, then you can iterate quickly and have fun doing it. So that's it from my side. I'm looking forward to your questions. Thanks.
Hey, Mark, thank you so much. It's quite interesting. We have some questions for you.
Sure.
Let's see if we're gonna cover all of them. The first one says, how do you validate a deep learning model as a diagnostic lab technique?
So yeah, it's a complicated procedure actually. So what we do is we make a CE label. That's a norm of the European Union. So, and to do that, you need to cover a lot of things. You need to have some quality control systems in place. You need to have a study usually. So you have a couple of pathologists that do the analysis with and without AI, and you compare that. That is at least similar results. And if you've done a nice study like that, then you need to write all of that up in a lot of nice regulatory documents. It's a lot of fun. And with that, you go to the regulatory body and you say, hey, look, this is our medical device description. This is what we did. We have the study results here and this and that. And then they give you the CE mark, and then you can sell that as a diagnostic technique. Yeah. But
Nice,
besides, so I mean,
summary.
what we also do, of course, I mean, it's a longer process to get this label. It's a lot of effort. So what you do in the meantime is you use lab develop tests. So the labs themselves, they can also validate the method internally, and then they can also use it in diagnostics without this label. But of course, then it's more work for the lab, and that depends on the customers. Some of them they're fine with it, but also even mostly the larger labs, they want to see a label.
Okay. The next one, how would you define the good amount of time to spend on hyperparameter optimization?
Yeah, that's a good question. I mean, so I think that really depends on your hyperparameter. If you're, I mean, what we usually do is you try out some small ranges, and if you see that has a large effect on the overall results, then of course it might make sense to spend more time there. But if you see, okay, the impact is small, then I mean, there's only so much you can do, right? I mean, this costs a lot of compute. You usually have many hyperparameters, and if you want to fine tune all of them, I mean, of course, if you want to do that, I recommend random search of hyperparameters instead of doing grid search, because with random search, you get better coverage of the parameter space. But yeah, it's definitely not easy to have a concrete answer for good amount. It's always a trade-off between compute time it takes you, and the time you have available.
Thank you. And I think this is the last one we can read. Are you using traditional CI like GitLab CI for all the machine learning integration and delivery stages, or you're also thinking about using more specialized platforms like Kubeflow?
So currently, we're well covered with GitLab CI. That said, of course, as I've shown, we use DVC for the more machine learning aligned pipelines. So for having code dependencies and steps that run one after one another, we use DVC. But for everything else, we use GitLab CI. But yeah, it might be worth thinking of something more specialized in the future. But so far, this combination really serves us well.
It's working fine.
Yep.
Okay, there is one more question, but the discussion can continue in the breakout
Oh,
room, the Parrot.
yep.
Thank you so much, Mark.
Thanks a lot, Santiago. Bye-bye.
Bye bye.